So in this part we are going to discuss some complex integrations, and yes, we are going to start our discussion with a simply connected domain. Okay, and then we'll discuss Cauchy theorem, okay, its proof and questions on it. So first of all, if we want to understand what is simply connected domain, so for that I am going to make two pictures over here. Yes, you can see this is your figure number 1, okay, and another figure is this. Okay, so if you will try to shrink, okay, then you can see I am talking about this region. Okay, when I am talking about the domain, then this region, okay, this annulus you can say, and here this. Okay, so if you will shrink the figure number 1, then you are going to get a hole. Okay, you cannot shrink to a point without hole due to this. So that's why we will call it not simply connected. Not simply connected. Why? Because it cannot be shrunk to a point without hole. But here you can see it is simply connected. No problem, because you can shrink this figure to a point. All right, yes. Now I would like to observe one more interesting fact over here. Okay, you can see if you will take any closed curve inside this domain, and then if you will try to see its area, then you can see its area is outside the domain, outside this white portion. Okay, this area you can see this is not the part of the domain. Okay, but in simply connected domain or simply connected region, you can see if you will take any closed curve, then the whole area obtained by this will lie completely inside it. Okay, so I think now you can easily write the definition of simply connected domain, isn't it? Simply connected domain means what? Simply connected domain or region means what? Which can be shrunk to a point without hole. And one more thing was what? Area of any closed curve lies within it. Okay, and what would you like to say for domain which is not simply connected? Not simply connected means what? Not simply connected means what? Cannot be shrunk to a point. Shrunk to a point without hole. Okay, and one more thing, when you will try to make a figure inside it a closed curve, then the area goes outside the domain, then it is called not simply connected. Okay, so I hope this is quite clear. Now I would like to write some results. First of all, let's write this Cauchy theorem or Cauchy's theorem. What is it? So let f is defined and analytic on simply connected domain. simply connected domain. Okay, so domain means what? Certainly it is open and connected. Okay, and f dash is continuous. F dash is continuous in D. I mean to say the partial derivatives of f will be what? Continuous in D. Then along any closed curve in D, any closed curve gamma in D, the integration over gamma of f will be what? 0. This is what? Cauchy's theorem. What they actually want to say? Actually they want to say that if you will take an open and connected, okay, simply connected domain, let's say this kind of domain. Alright, if your f is analytic in this domain, then along any closed curve inside this, if you will try to find the contour integral, then the integral will be nothing but 0. This is what? Cauchy's theorem. So let's go to prove it. Okay, so for its proof, a very simple proof, you can see what we have to say. We have to prove that f of z dz, this is going to become 0, isn't it? Because we have to prove this integral over f is equals to 0. So this is what? Integral over f of z dz in a proper way, if we will write. So you have to prove this. And what the things are given? You are given, you have a simply connected domain, and this is any closed curve gamma inside it, and then you have to prove that this is going to become 0. Right, integral over this is going to become 0. All right, so for this, what shall we do? We people know that z is equals to x plus iota y, so certainly your dz will be what? Dx plus iota dy. Okay, and what is your f of z? Your f of z is nothing but u plus iota v. So hence you can see what? How it's look. Certainly it will on this gamma you can see what? F of z plus dz, so it will become u plus iota v in place of f of z, and in place of dz you will write dx plus iota dy. Then what shall happen? You can see what? Certainly it will become u dx and iota square v dy. So we will write the real part as u dx minus v dy. Alright, and plus iota into, you can see u into iota dy, so it will become u dy, and plus iota into v dx, so you can write it as v dx, isn't it? This is the thing. Alright, and now from here you have to use the Greens theorem. Okay, what is Greens theorem? I hope many of you already know. Greens theorem is what? If you have a closed, you have to integrate over a closed curve C, and you are given p dx plus q dy, which p and q are continuous function and their partial derivatives also exist. Then this is equals to a double integral over the region R, and certainly del q by del x minus del p by del y. Okay, and at last, yes, what the thing? Dx dy. Okay, so yes, there is a very beautiful relation between this closed integral and this double integral, we already know. So hence you have to use that over here, because u and v have also continuous partial derivatives, because it were there in this that f dash is continuous. Okay, so certainly that is going to happen, and we are able to apply this Greens theorem beautifully over here. Okay, so you can see what? Here is u dx minus vy okay, v dy actually, not vy, just a second, it's v dy, it's what, v dy. All right, so we'll apply that one over here, so it will become del minus del v by del x. Okay, double integral, it will become minus del v by del x, so it will become minus vx and minus what, minus del u by del y, so minus uy. Okay, and thereafter dx dy and plus iota double integral, it will become what, u dy plus v dx. So once again it will become what, vx vy and minus ux. Okay, vy means what, del v by del y minus del u by del x, you can easily see, and certainly here dx dy. Now Cauchy Riemann will come to encounter. Okay, you can see what, over the domain you can see this is minus vx and this is minus uy, so uy is equals to, we know, minus vx. Okay, so here minus vx is already there, and minus minus plus vx, dx dy, isn't it, and plus iota, once again vy minus ux. Okay, this is the given thing, right? So from here you people know that ux is equals to vy, so it will become vy minus vy dx dy, isn't it? So finally you can see this is going to vanish, this 2 will become 0, this 2 will become 0, so finally we have what, 0 and nothing more than this. So certainly we can say what, yes, this theorem has proved beautifully. Now let's go to apply this on a question. So let's go to take a question for Cauchy theorem. All right, so think you have to integrate over the curve C. Okay, and you have to integrate this one, e to the power az upon z minus pi iota dz, and where what is your C right here, your C is nothing but an ellipse, and how it is written, mod z minus 2 plus mod z plus 2 is equals to 6. Okay, this is the thing. So first of all we will analyze this domain. Okay, we will try to analyze its domain. So first of all let's go to analyze whether this pi iota will lie inside it or outside it. Okay, so it will become mod z minus 2 plus mod z plus 2 is equals to 6. So yes, you will write x plus iota y minus 2 plus mod x plus iota y plus 2 is equals to 6. All right, so yes, we will get what, mod x minus 2 plus iota y and plus mod x plus 2 plus iota y is equals to 6. So finally what the thing we are going to get, x minus 2 whole square, okay, modulus plus y square and plus under root x plus 2 whole square and plus y square is equals to 6. We want to write this in Cartesian form so that we can see the location of pi iota. Okay, so what shall we do, we shall take x minus 2 whole square plus y square is equals to 6 minus under root x plus 2 whole square and plus y square. We'll square both sides. So after squaring both sides, what shall we get, x minus 2 whole square and plus y square, and the square of 6 will be 36 and minus 2 6 are 12 under root x plus 2 whole square, all right, and plus y square and plus what the thing will be there, its square will be x plus 2 whole square plus y square, so x square plus 4x plus 4 plus y square. Yes, this will be the thing, isn't it? Yes, is this clear? Okay, So now let's see what are the things that is going to become cancelled. X square minus 2ab, so minus 4x plus 4 and plus y square is equals to what? 36 minus 12 under root x plus 2 whole square plus y square and plus, yes, these are the thing, x square plus 4x plus 4 plus y square. So y square will be cancelled, 4 to 4, x square to x square, all these things will be cancelled. And finally we will get what? Take this square root into this side, so it will become 12 under root x plus 2 whole square plus y square, and let's say this will become what? Yes, 36 and minus minus plus 8x. Do you know this 4x and this 4x will add to, okay, and thereafter we can take 4 as common, isn't it? So it will become 4 under root x plus 2 whole square plus y square, and this if we will take 4 as common, then what shall happen? Only 3, isn't it? Here will be 3 only, okay, and here divided by 4 it will give you 9, divided by 4 it will give you 2x, isn't it? Yes. So now you will square again, squaring again, you are going to get 9 into x plus 2 whole square, so x square plus 4x plus 4 plus y square is equals to, you will get 81 plus 4x square and plus 2 2 ja 4, 4 9 ja 36x. All right, so finally you are going to see what? 9x square minus 4x square, 9 4 ja 36x. All right, so plus 36x and 9 4 ja 36 plus 9y square is equals to 81 plus 4x square. Okay, 4x square has already taken into the LHS, okay, that is here minus 4x square. So okay, and yes, 36x were there, so these two will be cancelled. All right, okay, we had already transferred this earlier, I don't know why, but yes, we had done it. So it will become what? 5x square and plus 9y square is equals to 81 minus 36. So it will become what? 5x square plus 9y square is equals to 45. Okay, and now 5x square divided by 45 plus 9y square divided by 45 is equals to 1. So it will become what? X square by 9 and plus y square by 5 is equals to 1. So finally we can see what? This is x square by 3 chi square and plus y square by root 5 chi square, and this is equals to 1. So when we will try to draw the picture, then how it looks, it will become, isn't it, minus 3 plus 3 as major axis, okay, and root 5 minus root 5 as minor axis. And when we are going to draw the ellipse, very bad, but yes, you can understand this egg. Okay, so yes, this is the thing, this is your ellipse, but you can see what? The point where what? We have to integrate for this pi iota, but where is your pi iota? What is the location of this? Your root 5 is what? 2 point something, 41 something like that, but pi is what? 3.41. 146, things like this. So you can see this point is outside this domain. Okay, so if the point is outside this domain, it means what? Certainly over this your function is analytic everywhere, and as your function is analytic, therefore according to the Cauchy theorem, your integral will be what? Yes, you people are saying the right thing. Your integral will be what? 0. Okay, so yes, your integral will be 0. Okay, so this was a Cauchy's theorem. So we can say what here? We can observe something. If you have a simply connected domain, if you have a simply connected domain D, okay, let's say this one, and if you want to find integration along any closed curve inside it, okay, then certainly that will be what? 0. But there are some more statements shared by Cauchy-goursat, okay, which is called Cauchy-goursat theorem. Okay, yes, some extension of this statement is also there. Think your f is what? F is analytic in simply connected domain D everywhere except some finite number of points. So let's make the picture at first. Okay, think your picture is like this. Simply connected domain, certainly it can be shrunk to a point. Okay, simply connected domain, and there are some point where the function is not analytic. Let's say these are the points, but it should be finite in number. Okay, and if one condition is going to impose that in the neighborhood of these points your function is bounded. Okay, in the neighborhood of these points your function is bounded. Okay, in the neighborhood of these points your function is bounded. If we will apply this condition, but let me write that condition, but in the neighborhood of these finite number of points, f is bounded. Okay, f is bounded, then integration along gamma f dz will be again 0, where gamma is what? Any closed curve inside this domain. Okay, so you should remember this extension as well. Okay, this is called Cauchy-goursat theorem or Cauchy-goursat lemma. All right, now let me give you an example to illustrate this beautifully. If I will give you a function f of z is equals to sine z by z, if your z is not equals to 0, and let's say 5 if z is equals to 0. So you can see this here is a singularity at 0, removable singularity, and therefore what shall you say? This function is analytic. Let's say you are given this domain which contains 0 as well. Okay, but this function is not analytic at 0, analytic everywhere except 0. Okay, so where it is not analytic is what? A single point, finite number of point. Okay, so if you will try to find its integration along any closed curve in this, inside this, then certainly you are going to get 0. Okay, according to Cauchy-goursat theorem, you can say its integration will be what? 0. Okay, yes. Now one more thing is what? Think you are given a simply connected domain. You are given a simply connected, this is also a result. You should keep all these things in your mind. Think this is your simply connected domain, certainly open also. All right. And at some finite number of points, let's say these are the points where the function is not analytic. Okay, these are the points where the function is not analytic and it is finite in number. Okay, but in the neighborhood of these points, your function is bounded. This is the neighborhood of this point, and in the neighborhood of these points, your function is bounded. Okay, like in the above example, you can see in the neighborhood of 0, your function were what? Certainly bounded, isn't it? Because their limit will be what? Finite. So yes, so you can see in the neighborhood of all these points, your function is bounded. Then let's say this is your initial point and this is your terminal point. So no matter if you will go along the curve gamma 1, okay, or you will go to this B along the curve gamma 2, your integration will be what? Same. Okay, so these are few results. Okay, and in the next lecture I will come up with Cauchy integral formula and many problems on that. So if you want to say anything, then you are welcome in the comment section, and you can check the playlist for the previous lectures. Okay, certainly you should check the playlist. Thank you very much everyone.